A good exercise is to prove for yourself that indeed this cannot happen when A and B are distinct. Hint: if you want to prove it, use what should you use? Right. The result that we got about conjugating different isometries. So, for instance, you can rewrite, if you multiply by row A on the left, then you can rewrite this equivalently as row B cannot be equal to row A, row B, row A inverse. And why can't that be? Because you know how to conjugate a rotation. So you know that this one is go ahead and finish the exercise. So what does this imply for us? It means that if we have a group of finite isometries which consists solely of rotations, then all rotations must be about the same center. Okay, let's now figure out what angles can we have. It's clear that we can only have rotations about the same center A, but by which angles? Well, first of all, if we have row A phi in our group, then we must also have row A minus phi. So what does it mean? The inverse, correct? That's row A phi inverse. If there is a rotation in the group, then the inverse must be there as well, but the inverse is just rotation by the negative angle. What does it mean? It means that if we have some other rotations, we can always subtract a phi. If phi is one of the rotations, then we can always subtract this angle. What else? Well, let's write any rotation in our group as rotation by an angle where phi is between 0 and 360, less than or equal than 0. So any rotation, so here you have to finish the exercise. And here we must be able to write any rotation, any row can be expressed, can be written as rotation by an angle between 0 and 360. Alright. Now let's choose the smallest out of all our rotations. After all, our group is finite, so we can always choose the least. So let phi be such angle that is the smallest of all our rotations after all of them are written in this way. Let phi be the smallest angle among all rotations in G. Smallest positive angle. So what does it mean for any other angle in the group? So let's say that alongside the rotation with the smallest angle, let's call it just a row. So we have row A phi, rotation by the smallest such angle, and that will just go by the name of row. Let's say that alongside with this basic smallest rotation, we consider some other rotation by angle psi. What can we say about this angle psi? Well, one thing we can say is that this psi is, of course, is in between 0 and 360. So it is in some limited range, right? So now let's try and find this psi, just like we do when we need to find the line in Africa. We just have to divide Africa into some subdivisions and let's do it using our smallest angle phi. So if we take a multiple of phi, maybe 2 times phi or 3 times phi, at some point we should be able to reach and surpass psi. So if we subdivide everything from 0 to 360 into phi, 2 phi, so on and so forth, k times phi, then at some point we should be able to catch up with psi, no matter how big or small it is, and maybe in the next step overcome it. So our psi should be somewhere in one of those intervals. Where exactly? I claim that it cannot be inside any of those intervals. It must be on the edge of one of the intervals for some k. Why? Because suppose it's in the middle. Suppose psi falls inside, strictly inside, not on the edge of one of those intervals. From k phi to k plus 1 phi. This cannot happen. Why? Because then if we subtract, let's look at the rotation by psi minus k phi, this is just rho psi composed with rho phi inverse taken k times. So since both rho psi and rho phi are in our group, then this rotation also must be in our group. And yet the angle will be positive and less than phi, which is impossible. So it can't be in our group, so psi may only be on the edge of those subdivisions. So there exists some integer k so that psi for any psi that we take is a multiple of smallest angle phi. That means the whole group consists of multiples of rotation rho composed with itself k times several number of times. So that means that the whole group G is just generated by a single rotation rho. And of course, since it's finite, then we have to have at some for some n, rho n is equal to identity. So finite cyclic group of rotations which we called Cn. So that is the case when our group consists only of rotations. So now let's assume that there is at least one reflection in the group as well. So assume there is also sigma, a reflection, in addition to any possible rotations. So case 2, there exists at least one reflection in the group. So let's repeat that case 1, rotations only, was concluded as G is equal to rho for some rotation cyclic group on n rotations. So some smallest rotation such that rho to the n is equal to identity. So that's rotations only.